Hi everybody. Today I would like to do a last part of this chapter, that is optical instruments. Let me do a brief recapitulation of last class and before last class. We talk about three important concepts, that is reflection, refractions and dispersions. So we have gone a little detail about all these three concepts. So today what we are going to do is we are going to apply all these three concepts and try to understand optical instruments. So in our syllabus we have only two optical instruments, that is microscope and telescope. So I shall start with microscope. Microscope. So let me start microscope something like this. So let me say this. First I will just give you an explanation of the term. Micro means a tiny object, micro means a tiny, very small, and scope means to see or to see, right? So therefore the microscope is an optical instrument which is used to see a tiny object or tiny particles, whatever, right? So therefore I would like to start microscope in a stepwise. So first I would like to start with a magnifying glass, which is a simple microscope, which we call a simple microscope. Many a time we call it as a magnifying glass or magnifying lens. So normally a simple microscope or magnifying glass consists of a single convex lens or converging lens with a short focal length. Alright. So now we look at here. Whenever we talk about optical instrument like microscope and telescope, we normally discuss two important parameters, that is magnification, alright, for microscope and for telescope, and then we talk about resolving power or resolution. So these two parameters are very important, essential for microscope and telescope. So this time we will discuss only magnifications. Why? Because the ray optic is ray optic can explain a magnifications, however ray optic cannot explain resolving power. Alright, so therefore you should keep in mind that magnification and resolving power, and this time I will be discussing only magnifications, and resolving power we will do in a next chapter, that is wave optics. So look at here. Now I shall start with a simple microscope. And simple microscope, I told you before, is a magnifying glass which consists of a single a short focal length convex lens. Alright. Then whenever we talk about microscope or telescopes, we talk about, maybe you have done this in class 10, about accommodations. Alright. So we talk about near point, we talk about far point. This is what we call a near point. This is a near point, which is normally denoted by D, which is of 25 centimeter, and this is the nearest distance which we can see comfortably. Alright, and this is what we call as a near point. And again we talk about far point. Again, this is the furthest point which we can see comfortable, and which is normally called as infinity, denoted by infinity. Alright, so this a very important point. Why? Because look at here, when we see through magnifying glass, and the image of an object is going to emerge, and we are going to make sure that either you are going to keep image at near point or at far point. These are the two options we have. Alright, either I am going to put image at near point, or I am going to put image at a far point. So therefore, whenever we talk about a microscope or a telescope, we have two options, right? for keeping image either at near point or at far point. Alright. So let me start. For magnifying glass, normally how we use magnifying glass is we used to keep a magnifying glass, or we used to bring object very close to our magnifying glass, either at focal point or at a distance a little less than focal length. All right. Why this is important is that when we see, we should get a virtual image, erect, magnified, enlarged. So this is what we have. What I have. I have a lens. I see through lens. This is an object, and this object should be either at focal point or at a distance between focal point and optical center, right? So that we get image erect and virtual enlarged. This is what you should keep in mind. So now look at here. What I told you is I can have a magnifications keeping image at near point. I can have a magnification keeping image at far point. I'm going to discuss both. So first, I would like to start with image. Let's say magnifications for image at near point. Image at near point. This is the ray diagram. This is the ray diagram. So look at here. Whenever we talk about magnifications, magnification is equal to h prime divided by h. H prime is the height of an image. This is the height of an image. Height of an image. And this is the height of an object. And also we can represent magnification in terms of V by U. We can also represent magnification. This is an object distance, image distance. This is an image distance. And this is an object distance. Alright. Now look at here. Now what I'm going to do here is, I'll use a lens formula which says that 1 by f is equal to 1 by v minus 1 by u. Alright. So therefore, 1 by u is equal to 1 by v minus 1 by f. Alright. And now what I'm going to do is, I have these equations, n is equal to v by u. I'll put the value of 1 by u, which is equal to v, 1 by v minus 1 by f. Alright. Finally, I get 1 minus v by f. Okay. So now, I told you just now that I'm keeping image at a near point. I'm keeping image at a near point. So if an image is at a near point, the distance is d. Alright. So therefore, I say since v is equal to minus d, y minus, this is sign convention I have used. So therefore, n is going to be 1 minus d divided by f. Alright. So finally what I get is, I'm going to write using red pen, 1 plus d by f. This is the answer. So this is the magnifications. So the magnification for a lens, magnification produced by a lens when the image is at a near point is given by this. I'm going to write here again, very important, 1 plus d by f. D is the distance for near point, f is a focal length, and there this is how we get it. This is magnification. So this is the magnification for an object at keeping such that we keep object such that image is at near point. Alright, this is, you should keep in mind. And now what I'm going to do is, now I'm going to do magnification for image at far point. So magnification, when I put magnification, when I find a magnification for image at a far point, I write here number 2 magnifications image at far point, image at far points. Alright, so that means I'm going to keep image at infinities. So what I'm going to do is I'm going to keeping image at infinity by putting object at focal points. That means I'm going to put object at focal point. I'm going to put object at focal point. I'll show you a ray diagram. This is the point. This is the ray diagram. This is the ray diagram. This is the ray diagram. And I'm going to put object at focal points, and then image would be at infinity, and magnification is we are going to find out magnification, right? So now for this we are going to use what we call angular magnification. So whenever we talk about image at a far points, all right, we find angular magnifications. We always find angular magnifications. All right. So whenever we try to keep image at infinities, magnification is always angular magnification. So what is that? I say this angular magnifications. This angular magnification is defined as, all right, theta I divided by theta O. I'll explain you what is theta I and what is theta O. The angular magnification is defined as angle, the ratio of angle subtended at I by the image, alright, to the angle subtended at I by the object. So this is angle subtended at I, alright, angle subtended at I by the image, when the object, let's say when the object is at U. Object is at U means object I'm going to keep it at F. Now next point is, what is this? This is the angle subtended at, let's say I, at I by the objects when object is kept at G. So this is what we have. So this is theta I, other one is theta naught. This is theta naught. So this is that I'm going to keep object at a distance D, and I see keeping a distance D, and what is the angle back by I with respect to H. So this is what we call as theta naught, and this is theta I, angle subtended at the I by the image, all right, or by the object when object is at focal point. This is what we are going to do. So how are you going to find out? Simple. I'm going to say 10i. What is 10i? 10i is going to be h divided by f. 10i is going to be h divided by I. Since theta is small, 10 theta I is equal to theta I, which is equal to h divided by f. Now what about 10? What about 10O? 10O is equal to h divided by d. So theta is small, so 10O is almost equal to theta O, which is equal to h by d. Alright, now what is the angular magnification? So angular magnification, I'll write here, this is angular magnifications, theta I divided by theta naught, which is equal to, what is theta I? H by f. And what is theta naught? Into by g by h. Cancel out, therefore m is equal to g by f. So this is magnifications. This is magnifications. Now I would like to write here, this is magnification for near point, and this is now m is equal to d by f, magnification for point. This is for simple microscope. Now look at here the limitation of simple microscopes, right? I can't go on increasing magnification. I can go on and at most I can go up to 9. At most I can go up to 9. So maximum I can go up to 9. Alright. So we can't go and find out get a focal length which is extremely very small, right? I can for practical purpose in practical I can get a converging length of focal length 1 millimeter. It's not possible. I can go up to maybe 2 centimeter, 5 centimeters, or something like that. Therefore, this is the limitation for simple microscopes. So the magnification is limited only up to 9 or 7, whatever, right? It's very difficult to go beyond 10. Alright, so this is a limitation of simple microscope. Now, you would ask me, why, what is the difference between keeping image at a near point and far points? So, look at here, if I go on with keeping image at near points, this get a strains. I get a strains. Alright, because it is close. So therefore, we normally advise, alright, keeping image at a far. Why? Because your eye get relaxed, so you can view object for longer period of time. Alright, so therefore, we prefer keeping image at a far point than near point. Alright, so this is for simple microscope or magnifying glass or magnifying lens. Now what I'm going to do is, since we got the limitation, or we know the limitation of simple microscope, now we would like to move to a compound microscopes. Alright, compound microscopes. So this is what we have. Compound microscope. So, what is the difference between a compound microscope and a simple microscope? So, compound microscope consists of two converging lens. In case of a simple microscope, it has only one magnifying glass or converging lens. So, therefore, since it has a two converging lens, the magnification can be compound, or a magnification can be multiplied, which we have done in a combination of lens. Alright, so therefore, this is a compound microscope. And again, in case of compound microscope, we have two options. Either I'm going to keep image at a far point, or I'm going to keep image at a near point. All right. So the advantage of compound microscope is, we get a magnification much greater than a simple microscope. All right. So let me explain you this. Compound microscope consists of two important lenses, that is objective lens. Objective lens is a lens which is close to an object, so this is called objective lens. And eyepiece lens. Eyepiece lens is a lens which is close to your eye. Alright, this is what we have. And compound microscope, the objective lens is normally of a short focal length. We prefer objective lens of a short focal length. Now look at it. It is something like this. I'm going to keep image. I'm going to keep object very close to an objective lens, but not beyond, but not less than focal length. And we are going to get enlarged image. So what we are going to get is we are going to find out magnification for objective lens. Magnification for objective lens, magnification for objective lens, and then we are going to find out magnification for eyepiece, again negative eyepiece, and then we are going to club together. Alright, so therefore, AB is object, and this is object height, whatever, right? And A prime, B prime is image of an objective lens, and which is enlarged. And now what I'm going to do is the image AB act as object for eyepiece, act as object for eyepiece. So this image acts as an object for eyepiece. And now again one more important point is eyepiece is more or less like your simple microscope. Alright, eyepiece is more or less like your simple microscope, which gives you inverted. This is already inverted, so you are going to get it inverted. And you have two options. Either you are going to bring this at infinity or at near point. Alright. So very simple here. Eyepiece act as a simple microscope. Act as simple microscope. Alright. So now what I'm going to do is I'm going to find out magnification for eyepiece, magnification for objective lens, and then we have already found the magnification for simple microscope, and we are going to combine together. Alright, so look at here. First I would like to find out magnification for objective lens, right? M naught. Magnification of an objective lens, M naught. So how to find out M naught? Again, M naught is equal to H prime divided by H. This is the magnifications. This is what we call as a linear magnifications. Other one is what we call as angular magnification, right? So this is what we have. However, now I just say I take this angle, beta, right? So I say 10 beta is equal to, this is H, this height is H, this is H, this height is H, and this distance is F. Again I say, this has a focal length of F naught, and this has a focal length of Fe. Alright. And distance between F naught and Fe is what we call as L, which is called length of tube length. This is called tube length. Alright. So again, I'll make it very clear. Objective lens has a focal length F naught, And eyepiece has a focal length Fe. And now first I would like to find out magnification of an objective lens. Magnification of an objective lens. This is magnification of an objective lens. So what is tan beta? This tan beta is going to be H divided by F naught. And then next one is tan beta is equal to H prime divided by, what is that? L. L is length of tube length. L is what we call as tube length. Okay, now again I just write here. If beta is small, then beta is equal to beta, alright, which is equal to H by F naught. Again, this is tan beta is equal to beta, L divided by H prime divided by L. So I compare these two. Equations. H divided by H prime is equal to when I compare these two equations, H divided by F naught is equal to H prime divided by L. And what is that? H prime divided by H is equal to L divided by F naught. Am I right? Okay. So what is H prime divided by H? H prime divided by H is what we call a M naught. So I'll bring here M naught is equal to L divided by F naught. Yes. So this is magnification for an objective lens. So I'll write at top, magnification for an objective lens is magnification for objective lens. Magnification for I write here magnification for objective lens is equal to L divided by F naught. This is done. Alright. Now this lens is already done. This part is already done. Now we are going to find out this. What about ME? ME. Alright. So now we would like to find out what is ME. So what is ME? So ME for ME, that is magnifications due to eyepiece. Magnification due to eyepiece. Again, we have two options, right? Since this act as a simple microscope, again I'm saying this act as a simple microscope. So we have already done. So for near point, magnification is going to be 1 plus G Fe. This is for near point. And for far point, alright, this is, so now look at here. For compound microscope, if a final image is at a near point, this for this case, compound microscopes, with the final image at near point, then magnification is going to be, look at here, this is equal to magnification due to objective lens multiplied by magnification due to eyepiece. This is how we find out. So this is equal to, how much is objective lens? Objective lens is this, L divided by F naught. And what about ME, eyepiece? Since this is for near point, this is going to be 1 plus GFE. This is what we have for compound microscope. Now I'm going to write compound microscope. Number 2, compound microscope with final image at far point. This would be again M is equal to M naught multiplied by ME. M naught remains same, that is equal to L divided by F naught. And what about ME? ME is going to be G divided by F. So this is the final compound microscope, right? So final, now I have already done in textbook. We have only done with the simple the image at the near point, and you can go on and get a image ray diagram for image, a final image at the far points. All right, this is the point. This is what we have. This is a ray diagram. This ray diagram is not there in your textbook. This is a ray diagrams where a final image is at infinity. Where final image is at infinity. This is the ray diagram where final image is at infinity. Alright. This is all about microscope. This is all about microscope. Alright. So now look at here. So microscope, I can go on increasing magnifications, right? So we have the 3 factors, right? This is 1 factor. All right, this all you should keep in mind, right? These all are the factors which affect the magnification of microscope. So maybe if you are taking biology, and then you may come across this in your lab. What is the magnifications for your compound microscope? All right. So this is all about compound microscope.